Hello everyone. Now we'll see the next unit, that is stiffness matrix method. Today I'll give you a brief introduction about this unit. So it is completely the inverse of flexibility matrix method. It is very simple and it is almost dependable on your slope deflection method. Slope deflection method in the unit in which we have seen this unit we have seen already in theory of structures 1, the very first unit in that subject. Okay, so it is defined as the force developed due to unit displacement. It is denoted by K, whereas flexibility was denoted by small f. Here flexibility is stiffness is denoted by K. Okay, flexibility is deflection per unit reaction, whereas stiffness is reaction by deflection. Okay, it is nothing but P delta. Okay, so here we know this equation. This is moment MAB is equal to MFAB or small MAB plus 2EI by L into 2 theta A plus theta B. This is our slope deflection equation. We all know this one, isn't it? So if you open this one, if you open the bracket, MAB plus small MAB plus 4EI by L. How 4EI by L? I have multiplied with this. I have opened the bracket. So 4EI by L into theta A plus 2EI by L into theta B. Okay. Similarly, we have MBA, that is moment from B to A. So MBA plus 2EI by L to theta B plus theta A, right? I hope you remember this equation. So from here, MBA is equal to MBA plus 4EI by L into theta B plus 2EI by L into theta A. Just open this bracket, this one. Okay, so capital MBA is equal to MBA, small MBA plus 2EI by L into theta A plus 4EI by L into theta B. Okay, the same thing we have written here, So we can write the same thing in matrix form, isn't it? So the same formula, see here, you consider this one and this one, this highlighted one, this one and this one. Okay, so now take here MAB, we have taken here MAB. From here MBA, it is MBA. Now here small MAB, small MAB, small MBA, small MBA plus, open the bracket. Now we can write here 4EI by L, 2EI by L, then 2EI by L, 4EI by L. In bracket we can write theta A, theta B. So if you open the bracket, you'll get the same two equations. This one and this one. This one and this one. Okay. Now if you further move across, we can make it as P dash. This one I can denote it by K and this one as delta. Okay. Now if I want delta here on the right side, or I want to make it as a subject, then what will happen? We keep it as it is. If you send this term toward left hand side, it will become P minus P dash. Then if you send K towards again on the right side, then it will go in denominator. Okay, so delta will be equal to P minus P dash into K inverse. Okay, this is the standard equation of your stiffness matrix method. Okay, now there are few steps involved in solving the problems in stiffness matrix method. Okay, so the very first thing in the first step is you have to determine the kinematic indeterminacy of the structure. How to find the kinematic indeterminacy of the structure? We'll see that. Now identify the displacement components and assign the coordinates. As in case of your previous case, in case of flexibility matrix, we used to denote node 1, node 2, node 3. The same thing will be denoting here wherever we are displacing. Now here in this case, in the previous flexibility matrix method, we were bothered about the deflection, right? YB, total deflection, is equal to Y1 plus Y2, isn't it? You might have remembered this one. Now here in this case, we'll be moving across the rotations. We'll try to rotate the joint here. So we'll see all the things. So identified the displacement component and assign coordinates 1, 2 and 3. Restrain all the displacement components to attain kinematically determinate structure. So this point also we'll see in the problem. We'll try to rotate the structure and we'll try to make the structure as kinematically determinate structure. Now in the next case again, release the displacement components one by one to develop stiffness matrix. Since in the previous case we used to apply 1 kilonewton reaction at each point, whatever the unknown forces were there. Now here we'll try to rotate by 1 radian, that is we'll try to rotate the figure, we'll try to rotate the joint by 1 radian, that is theta will be rotated. Now find the fixed end moments and external force or moments at the coordinates and represent it as p dash and p respectively. So whatever the fixed end moments, it will be denoted with p dash, whereas the final external force moment will be p dash. Okay. Knowing all the displacement, find out moments using slope deflection equations. So finally we have to use our final slope deflection equations which were there in the first unit of theory of structures 1. Okay. Then later on we'll go for the what are the properties of stiffness matrix method. It is a square matrix. Yes, it is a square matrix. Then it is a symmetric matrix as well. Since you can see here, see the matrix here, it is a square matrix as well as it is symmetric matrix. Now here the size of the matrix will be equal to degree of kinematic indeterminacy. That is same thing in case of flexibility matrix method. We have seen that the size of the matrix it will be dependent on statically indeterminate. Okay, here also it will be dependent on kinematic indeterminacy of the structure. The size of the matrix in case of flexibility matrix method, it was dependent on static indeterminacy of the structure, whereas here also the size of the matrix will be dependent on kinematic indeterminacy. Okay, now we'll see the problem. So problems we can see in the next class. It would be better if we try to solve the problem in the next class. Okay.